Hello again.
Blither,
Back again for part 2 of Equational Logic and Equality in Logic with Philip Zucker. I'm Cody Rue, and you're on the Church of Logic. All right, Phil was saying something interesting, but I hadn't hit record yet. And yeah, basically, I don't know if my intuitive justification of why it's decidable on ground terms is even right. Is there some... Yeah, all right. So let's talk about that, and let's also figure out whether there's some way to explain the more efficient algorithm, which is known as, I guess, the congruence closure algorithm.
Yeah, congruence closure, and it's also in some communities called an E-graph. It's a data structure that does the efficient version.
Okay, but it's not. It's the crucial data structure that allows you to implement this algorithm.
Yeah.
Okay. Cool. All right. So, what's the idea? What's the idea for congruence closure, roughly?
I think the idea for the E-graph is that you want to share as much as possible, and that, boy.
So yeah, I mean, the basic idea, as far as I can tell, right, is you want to know what things are equal, right? So you maintain a set of all the things you know are equal for each congruence class, right? So you have a bunch of terms that are equal, you put them in the same bucket. You need to have some way of representing that bucket. And then when you learn new facts, you look at new equalities, you learn new facts. Some of those buckets need to be globbed together, right? That's the union step. And then if you really, at any point, you wanted to say, okay, do I already know whether these terms are equal? That's the find step. So that's the union find part of congruence closure. Is you need to know if f of A is equal to g of B. You find on f of A, and you find on g of B, and you see if they have the same representative. And then maintaining these sets of representatives that's the union part. You have some big bucket where you have a bunch of terms together. They each have a single representative of like who's in charge, who's the representative of all those things that are equal. Does that sound about right?
That sounds about right. Let's change the episode to talking about imposter syndrome. Because I feel like I've been on 2 episodes now. Well, this is the 3rd, really, where it's like subjects I hold so near and dear to my heart, and I'll talk forever about them as long as there's not a microphone on.
Yes. The microphone is a cruel mistress.
Yeah.
It makes you second guess yourself. I found that teaching can do this as well, because people will ask questions or they'll be confused and you're completely tongue-tied. You just sort of like you don't remember what you used to know. But definitely that's not going to be the subject of this episode.
Oh, okay.
So I'm going to try to wrangle
all...
You have all this knowledge.
Yeah.
And it's also very fun to talk to you. So the combination of those two is just going to definitely... This is just like working.
Yeah, this is gold. This is gold.
So let's talk about... Let's go back to the non-decidable case. Though I'm not sure I'll be able to say everything we wanted to say. We'll make a 3rd episode. Let's talk about quantified equalities, like this group theory equality I was saying, where, if you have commutative groups, right, you have x times y equals y times x, or, x times the unit is equal to x. Great. So you have all these equalities, and you want to prove some new equality holds.
Yeah.
And basically people were trying to do this, for decades, in the 70s and the 80s and the 90s. They still try to, but some of these classic algorithms were invented then. And so basically what's the idea? How do you cope with this?
I mean, I think the basic method is just you just spray, and that's called naive completion, where like I would take these axioms and I would see if I can apply them to each other, and then I derive some new fact. And I keep like a big bucket of new facts. I never delete the old ones. I don't destroy the old equalities when I use them, and I just keep making more and more facts, and eventually, either I find the fact of interest, or I keep going forever, or I sometimes I just like can't find a new way to make a new fact. Sometimes I can have
Great. Great. That's insightful. All right, so I feel like rewriting is essentially the field of finding optimizations to this basic idea.
Yeah.
So
It's
what
reasonable.
what is an example of such an optimization?
Well,
If you had to, off the top of your head.
I mean, there is a notion that like you don't really want to keep everything around. Like it's so obvious that some things are like hyper redundant. I mean, if you somehow ended up deriving like a massive term equals the same massive term, like that's stupid to keep that around. That's like an obvious identity. Let's just lose it. But then there's also stuff of like you already have like a massive subterm, or a massive term is equal to some small term, and then that massive subterm appears in some other equality. You want to like get rid of it because like it's kind of wasted energy somehow. It's wasted like space.
Yes. So I would say conceptually this sounds like a notion of simplification. You want
Indeed.
to apply your equalities in a way that simplifies things.
Yeah.
And I think this is a very deep notion. It's essentially, tens of thousands of pages of research where you think about ordering. You think about simplifying things by making them smaller in this ordering. What's kind of cool is if the ordering is terminating, the simplification is kind of not too scary because you can apply it eagerly.
Yep.
And you end up with, you never put yourself in trouble, right? You can always keep simplifying and you'll run out of steam.
I mean that is the other obvious method, I guess. It's nothing's it both is obvious and isn't obvious, but like, an obvious method you might have if I had some big trigonometric expression and I want to know if it's equal to some other big trigonometric expression, I might just apply simplification rules to both sides a bunch, and if those two sides ever become equal, then we're good.
Cool.
But like
in the sense of they are the same term.
Yeah, if I can apply a bunch of simplification rules to literally the same term, that's great. But the thing is, simplification rules, as what people usually do there, is they destructively apply these rules. And actually, a bunch of trigonometric simplification rules don't have good properties of the way they like work with each other. Like it matters what order you use them in, and so on and so forth.
So we're reaching a term I wanted to bring up, but will probably be again subject of yet another episode. What is that property where basically the order doesn't matter?
Confluence.
Right, okay. So confluence is basically if you apply these equalities in a certain direction, always consistently like that direction, and regardless of how you do it, you'll end up at the same point eventually. That's confluence. And proving that property or taking a bunch of equations and orienting them so that the resulting system is confluent seems to be one of the fundamental themes of equational logic.
Mm-hmm. And that this process is what completion is usually described as. It's building this confluent system. But at the same time, the problem that's actually more interesting to me is this theorem proving problem of like deriving all consequences or something. And somehow these problems are very similar.
Right. Some subtle point that I'm going to briefly mention before we're kind of out of time is one thing that's interesting is you can't always orient the equalities such that the resulting system is confluent, right? Where you can apply these things without caring about the order. But what can happen sometimes is, if I just add this new equality, this derived equality, that's deducible but not included in my set of known equalities, then that creates a new rule, and with that new rule, it is confluent. And there's some systematic way of doing this, which I find fascinating. Some systematic way of figuring out what rules are missing for confluence.
I mean, to some degree, it's a little bit intuitive that like you might try and apply rules, find a case where they like, and that is what you're doing. You're finding these critical pairs of they went two directions. The order was showing the order mattered. Like if you use this one versus this one, and then we're literally just adding that rule into the system, saying that actually if you have this mismatch from the ordering mattering, actually those two are the same.
Yes.
And you add that as a new rewrite rule.
I like how you're using your hands as visual indicators. I understand this is not filmed.
The podcasts are an intrinsically visual medium.
Yes, exactly. All right, let's call it here for now. And there's plenty more to talk about, so we'll probably be back.